Welcome to Study Loop.
Problem 7.6. We have a crate of mass m that starts at the rest at the top of a frictionless ramp inclined at an angle A, or alpha, above the horizontal. Find its speed at the bottom of the ramp, the distance d from where it started. And it asks us to do this in two ways. So the first way, you're just going to set the potential energy to be 0 at the bottom of the ramp. So in order to do that, I'm going to write y equals 0 here. And then therefore we will be measuring the potential energy with respect to this point. So if the object is at this bottom of the ramp here, it's going to have potential energy of 0. So in order to do that, we're going to find the speed of the bottom ramp using work. So we're going to write work due to gravity, and that's going to be equal to the change in the height of the object. So we're going to write mg and y2 minus y1. Okay, so here we have y1, that's going to be where it ends. So we know that's going to be 0, but we need to find an expression for y2. So y2 is just going to be the position of the block at the top of the ramp. That's going to be its vertical displacement from the bottom with respect to the y equals 0 at the bottom. So we need to find an expression, and what we have available is alpha and d. So what I can do is I can write that y2 is equal to d sine of alpha. So just from your basic knowledge of triangles, in order to calculate what that distance here is from the top of that triangle here to the right angle here, you're going to take the hypotenuse and multiply by sine of this angle here. So that's going to be d sine theta. So in the end here, we're going to get mg d sine alpha. Okay, so that's going to be then equal to the negative of the difference of u gravity. And what we can do now is we can use that in our conservation of energy equations. So we have K1 plus U1 equal to K2 plus U2. Sorry about that. So we have that it starts at rest. So that means that this is 0. This K1 is 0. We know what the change in the potential energy is. So that's going to be equal to U1 minus U2. So we can just rearrange this equation to be U1 minus U2 equal to K2. Then we get mg d sine alpha, mg d sine alpha equal to K2. And then from there, you can we know what the expression is for kinetic energy of a single object. So then that's just going to be equal to 1/2 mv squared. And then from here, it's just solving for v, for the velocity. So that means that we get velocity is equal to the square root of 2g d sine alpha. Okay, so that's the problem for part A. So on a new page, we're going to do part B, but let's first look at what the difference is going to be. We have at the top of the ramp with y positive upward for part B. We're going to take what 0 is there. So for part B, and let's actually keep it on this page. It's going to be short. So for part B, we have the same setup, but right here is where we're going to have y equals 0. So we can do the same thing with the finding the distance from the triangle. But in this case, we're going to have our y2 be 0. In the same expression where y2 be 0, y1 is going to be below 0. So it's going to be a negative value. But we can just find what that distance is, and it's going to be the same distance because the triangle hasn't changed, but it's going to be negative. So y1 is going to be negative d sine alpha. But then what we have here is y2 minus y1. We have 0 minus a negative number. We're just going to get mg d sine alpha again because the negatives cancel out. And I'm sorry for looks a little nasty there. So if we have the same amount of work done, we should get the same result there for velocity. So that's going to be the same answer. Okay, then part C, why didn't normal force enter into your solution? Okay, so as the block is traveling down the ramp, the normal force is going to be perpendicular to the ramp itself. So we have the mass here, and we have normal force that's going to be perpendicular to the ramp. And since the actual motion of travel is down there, what we have is a right angle between the normal force and the actual direction of travel. So then when you have the work is equal to the integral of the force vector dotted with the displacement vector, the dot product between vectors that are perpendicular to each other is going to be 0. So that, therefore, the normal force doesn't compute into our expression for work.